All right, video over ionic bonds, and I guess specifically making ionic compounds, right? And I guess thankfully for us, ionic compounds are pretty easy to make. I don't know, I guess like to form, to create. Specifically for us, it's thinking about what are the formulas for these things? And you say, I don't know what that means. Well, let's talk about it, right? So I got this fancy new tablet thing I can draw on. Look at this. Let's try it out. Let's see how much better it is. I don't know. My handwriting's pretty bad, so let's see if it's any better. In any case, if I had a name, so say for example it was like sodium fluoride, right? Oh my god, this is maybe a little better. Maybe. In any case, sodium fluoride, right? That's a name of a compound, right? But you're saying, well, what is it? I don't know. It's sodium and it's fluorine, but what's the formula? How many sodiums, how many fluorines makes up this? Okay, and if you're saying, I don't know even by formula even then, imagine it as like a compound has elements that make it up, right? So like water, right? The name is water. Technically, you could call it dihydrogen monoxide, right? That makes it sound kind of scary, though. So we usually call it water. Water's formula, right, would just be H2O, right? And you're probably going, yeah, that's water, right? It has two hydrogens, and it has two, let's see if I can erase this, two hydrogens and two hydrogens, one oxygen. Sorry, I'm trying to get this thing figured out, the tablet thing, right? The little drawing tablet. So in any case, for sodium fluoride, how do we figure out what that is, right? The name water tells you nothing about it, right? You have no idea what's in it. Ionic compounds always have the name of the ions that are inside of it, okay? So sodium is Na. You say, oh, that's not that bad, right? And we'll do it the long way first. If you were saying, how do I figure out how many sodiums? You got to ask yourself, how many valence electrons does it have? It has one. You say, why does it have one? It's an alkali metal, right? Alkali metals always have one valence electron. They only want to give up one to behave like the noble gas that precedes them. So if sodium gives up his one valence electron, he gets the stability, essentially, of neon, which is the preceding noble gas. Okay, hopefully by this point you're like, oh yeah, I know that. Okay, and if you're like, what does that mean? Go watch some of my earlier videos, right, about electrons and valence electrons. But anyway, back to this. And you say fluoride. Well, fluoride ends in "ide," you might notice. And the reason this is important is it tells us that fluorine is in an ionic state. So specifically, we'd have an element called fluorine. And fluorine has 7 valence electrons, right? So he's got 7. And you got to think, who's buying, who's selling, right? Who here wants to give up electrons? Who here wants to gain electrons? And in chemistry, a metal is something that gives up electrons. So the sodium metal is going to take that electron and give it. More properly, it's fluorine taking it, right? But it also kind of works to think of it this way. So what happens here then? The sodium has given up his electron. He now has a charge because he is now an ion. Okay, he has a +1 charge. And to do a +1, we just do a plus symbol. You could put a 1, but we just usually don't draw it. Okay, so that's why I'm trying to teach you that way. All right, so here's my sodium with his +1 charge because he gave up an electron. He's positively charged. Now he lost negativity. And then the fluorine, or here I'm kind of combining the names, the fluorine has gained an electron, so now he has a negative charge, right? He has his 8 valence electrons, and he now has a -1 charge, okay? Basically, then you're saying, do these cancel out? Is everybody happy? Is the sodium happy? Is the fluorine happy? And then the answer is yes, they both have gotten what they want, which means how many sodiums are in sodium fluoride? Just 1. So just Na, and then the fluorine, of course, is still F. So this would be your answer. Sodium fluoride is NaF. Okay, and hopefully you're saying, oh, that's not that bad. Yeah, I mean, ones that start out really aren't that bad, and it'll get a little bit harder, but not horribly hard, if that makes any sense. So let's erase all this, like a giant eraser. Oh my lord. Okay, back to this. So let's do another one. What if I had, say, calcium? Let's say calcium nitride, right? Let's make it a little harder. Okay, so calcium nitride. That's being a little easier, right? What's the formula? And again, it's not obvious. You can't just look at it and say, ah. But what you can do is say, what are the ions? Okay. And again, I'll do it the long way, and then I'll probably use the same one for the shortcut. Okay. So calcium is going to have what charge? Calcium has how many valence electrons, I should say. Calcium is Ca, and he has 2 valence electrons. Meanwhile, I know it's nitride. It's an anion. He's going to be negative. It ends in "ide." You want to think of the element that sounds most like that. So nitride sounds like nitrogen because it's nitrogen in an ionic state, the anionic form of nitrogen. So what is that? That's going to be N, and he has 5 valence electrons. Okay. And what happens? Calcium says, hey, I got electrons, who wants them? And the nitrogen says, me, me, me. So the calcium will only give up 2, right? He'll only give up 2 of his electrons, which means the calcium is happy. He's done his job. He has successfully given up his 2 electrons, his 2 valence electrons, which means he gets to behave like argon, and he's pretty happy about that, okay? Meanwhile, the nitrogen is happy, sort of, kind of, but he is still missing, right, 1 more electron. He says, I want 1 more. And the calcium says, you're not getting 1 more. But luckily for him, another calcium can come in, right? Here's a second calcium with his 2. But he only wants to give 2, right? So he says, or he'll give 2, right? But the nitrogen only wants 1, I should say. So he takes 1. The calcium says, dude, I want someone else to take the other 1. I'm not just going to give up 1. So who comes along to save the day? Hey, look at that. Another nitrogen. And if you're asking, wait a second, are you like telling me that like this is literally what happens? It's more along the lines of you have trillions, quintillions, ginormous amounts of atoms. You're always going to have enough atoms for this to happen, if that makes sense. Picture it as just, this is like if it was going to go 1 by 1, here's what it would look like. It doesn't actually do it this way literally, but it might help you kind of slow it down to see it, if that makes sense. So the other nitrogen comes in. He has his 5, right? And he says, I'll take, right, 1 of those electrons, right? I'd like to gain 3. You only have 1 to give. So that calcium says, here, take this last one. Now that calcium is happy. But now the nitrogen isn't happy, right? So you're like, oh my God, it's going to keep going back and forth, back and forth. Don't worry, there's an end in sight. Because those 2 electron spaces, those 2 spaces for electrons, I should say, those 2 electrons that nitrogen wants to gain, can be given by, get this, a 3rd calcium. Okay, and that 3rd calcium is able to say, okay, you want 2? Well, guess what, buddy? I got 2 for you. All right. And if you're looking at this, you're probably like, okay, so what we're trying to do is get everybody happy. The calciums each give up 2, the nitrogens each gain 3, and that's exactly what happens. And to help you kind of plan this out, if that makes sense. And again, you don't have to do this. This is just a way for you to visualize it. We can think about our cation side. So here's my cation. Oh my. Okay, let's try that again. That was not the best. That was not the best. Let's try that again. I'll put it down here. Maybe that'll be easier to write. Let's see. So the cation side, right? Just using the vocab here. Cations are positive, and then we have the anion side. Okay, the negative side. So on the positive side, what do we got? We got 3 calciums, right? And you say, yup, that's true. What's missing? They've each given up 2 electrons, so each one has, get this, a +2 charge. Okay, so they've given up, each one has given up 2, for a total of what? The cation side has a charge of +6, right? That's like the positive side of the molecule, if you want to think of it that way. Technically, there is no side that's positive, unless it's 2 things, but it's okay for now. The anion side then is what? Well, I have 2 nitrogens, and those nitrogens have what charge? -3. How do I know it's -3? They gained 3 electrons. They gained 3 negatives, which makes them -3. And look at that. -3 plus -3 is -6. You say, oh, those cancel out. -6, +6. Exactly. So what's your answer? You say, this looks good. Your answer would simply be, hey, how many calciums do I have? I got Ca3, and then I have 2 nitrogens for an answer of, oh, wait, let's try that again. That was a horrible circle. Let's try that again. For an answer of calcium nitride, Ca3N2. Okay? So that's really what it comes down to, is just knowing what the charge is for both the cation and the anion and getting them to cancel. As a shortcut, let me show you a way that can save you a lot of time. Okay, so this is like a shortcut. It works, but be careful with it. So let's talk about it. Instead of me drawing out the electrons, I say, look, I know that calcium is going to have a +2, okay, because he has to give up 2. That's all he's going to give up. So it's got to be +2. And nitrogen is going to gain 3, okay? So I can do this. And you say, well, okay, what does it do for me? There's a little bit of a math trick here where I can take the 3 and I can basically say that's going to go down here. That's the subscript for calcium. And I can take the 2 and bring it down here for the nitrogen. And what do you get if you do that? Well, hey, look at that. You get the same answer, Ca3N2. And it's correct. And it's not like it's correct only in this case. It's not like it's a happy coincidence. It's true for all ionic compounds. Okay? It's pretty nifty. All right? And the only thing you got to be careful with is that when you do this, you have to make sure that the subscript numbers cannot be reduced. AKA 3 and 2, I can't divide those by anything. They don't have any common factors, okay? Which means I can't divide them by anything, right? I can divide it by 1, but that doesn't change them, right? So because that's true, this would be correct. And the reason this is correct goes back to this, okay? So like this is a shortcut that happens to give you the correct answer because of a cool math trick, if that makes sense. Basically, it has to deal with what's called a common multiple, but anyway. The premise is that you end up getting this answer, okay? And you're like, that saves me time. I like it. You got to be careful because if you do this trick, let me scoot over here. Let me erase all this, right? Oops, let's not make a giant green dot. Try that again. There we go. Okay. There we go. Perfect. You know that scratching noise in my writing tablet. Get back to this. Not a giant green. But let's pick one that maybe it works, but you got to be careful. Because it always works, but you got to be careful with the answer. So let's say you had, for example, aluminum phosphide. Okay, so if I gave you aluminum phosphide, you're saying, yep, aluminum phosphide. Now, aluminum is a metal, but it's in the P block. Okay, it's number 13. It's right next to silicon. It's right below boron. Okay, it's in the P block, which might make you think it's a nonmetal, which is reasonable. But there's like that staircase thing in the P block where metals are on one side, non-metals on the other side. Aluminum's on the other side, aka the metal side. Okay, and aluminum is always going to have a special charge. I shouldn't say always, but very rarely is he not. His charge is going to be, in this case, Al plus 3. Okay, it makes sense why he gives up 3, by the way. If you're like, how do you know it's supposed to be 3? Because he has a p electron. He has 1 p electron in the 3p, and then he has his 3s electrons, which means what? He wants to give up 3, right? He has 3 valence electrons. He's a metal. He wants to give up all 3. Okay. Can you make aluminum have a +1 charge? Yeah, you can. But again, let's not get too into the complex here. Let's keep it the simple for now. So Al plus 3, and then phosphorus is phosphide, right? Except he has a -3 charge when he's phosphide. You say, do the crisscross. It saves me time, right? Do that, bring them over. So I'd say, okay, the 3 goes here. By the way, notice I never put the negative down. You can't have negative of something. I can't have absence of phosphorus. That doesn't really make sense. That sounds like a novel, absence of phosphorus. I don't know. That sounds like a book title. But anyway, if you did this, you'd say, I got it. It's Al3P3. But if you're a clever cat, you're going to say, wait a second, 3 and 3, I can simplify 3 and 3 to what? Simply ALP. Okay? AL3. All right. The 3 and 3 you can simplify to 1 and 1. Right? You can divide 3 and 3 by 3 to get 1. 1 and 1. Okay? And if you're saying, well, how do I know that's right? I don't know. It just doesn't look right to me. Well, then do it the old-fashioned way, right? The old-fashioned way, of course, would be, hey, aluminum has 3 valence electrons. Phosphorus has 5. And then you say, hey, aluminum's a metal. He's going to give up how many? In this case, 3. And will you look at that? It's a perfect match, 3 and 3. Okay? So that's why it's ALP. Okay, not Al3P3. And yes, Al3P3 is wrong. You can't do it. It's incorrect. That's not what aluminum phosphide is. It's going to be ALP. Okay, so that's how you do it. So hopefully this video makes sense. Hopefully just going over how to form ionic compounds, it makes sense. You might ask, what about covalent compounds? There's a lot more versatility to those. So you can use charge, what's called oxidation state. You can use that to predict what's going to be made. But covalent compounds have more versatility. So it's not always going to follow these patterns that you're seeing for ionic compounds. That's why ionic compounds are a little bit easier to work with, if that makes sense. Whereas covalent compounds can be a lot messier. Okay? If you're like, prove it to me. There's this class called organic chemistry you take in college. It's 2 semesters long, and it's hard. And it's all about how carbon loves to bond with lots of things and lots to do with special bonds and crazy bonds, right? Because they're mostly covalent. Carbon tends to make covalent bonds. The moral of the story is ionic compounds are easier, okay? I'm not saying everything is easy with them. I'm just saying like forming them is easier, okay? Covalent compounds gets a little messier, okay? So hopefully this all makes sense. With that, I'll keep this video pretty short. Again, just talking about how to form these compounds, okay? So let me close out the video in theory. Have a good rest of your day.